Good afternoon, everybody. I'm Payman Byron, the chair of SAICE Structural Division. Thanks for joining us today, and I'd like to start by complimenting and wishing you all the best for New Year and 2022. This is the first of many lectures that we're going to organize for this year, and I hope that you enjoy the lecture. Today's lecture is the third of a series of lectures that we presented on designing connections and detailed designing, advanced designing of connections. We are assisted by Hilti, and we thank them for their support. We have two presenters today. Rishan is the head of marketing, technical marketing for Africa and Middle East, and we have Dursun, which is the head of technical and marketing for Dubai, Middle East, and Asia. And they joining us today to present the last of the series of these lectures. If you missed the previous two parts, we have them loaded in our YouTube channel. So you're more than welcome to watch the previous ones there. And what I do is I'm going to, in the Q&A, I'm going to post the link. So later on, if you would like to go back and just, have a look, listen again, or just to see what was, in case you missed the previous ones, they are there. So with that, I would like to hand over to Rishan and Dursun. Welcome, Dursun. We hope that we have you one day in South Africa in person, we look forward to that. But thank you very much for joining us from Dubai. And Rishan, thank you very much. I'm going to hand over to you.
Thanks, Payman. Good to see you, by the way. We haven't seen each other this year.
Thanks, Payman.
Yeah, as ever, a wonderful introduction. Welcome, everybody. I never know when it's too late to say Happy New Year and all the best for the year ahead, but since Payman beat me to it, Happy New Year to everybody on the call. Thank you for taking the time to join this third lecture that we're hosting from Hilti's perspective regarding advanced connection design. Fethi, if you can share your screen. Today's session is an interesting one. It's sort of a closing the circle or closing the loop in terms of what we've been discussing over the past few months. As Payman mentioned, if you haven't attended either of the previous two lectures, you're free to view it through the SAICE YouTube channel. What I'm going to take you through in this introductory part of the session is maybe just a quick recap on how we ended up where we are today and a bit of a teaser before we go into the session today. So as Payman already introduced us, I'm Rishan Manilal, Head of Engineering in Hilti South Africa. And this is my colleague Dursun Fethi Aktas, affectionately known to us as Fethi. So you guys can refer to him as Fethi if you like. He's the Meta Technical Marketing Manager. So Meta represents our Middle East, Turkey, and Africa region. And it's the reason it's dark where Fethi is because he is 2 hours ahead of us in Dubai. Hope all is well there, my friend. And as Payman said, hope to see you soon in South Africa. Cool. Next slide, please, Fethi. Cool. So as I mentioned, this is part 3 of a 3-part series that we've been hosting, and the first part, just in review, was basic walkthrough to post-install anchor systems. In that session, we spoke about the various types of anchors, chemical anchors, mechanical anchors, the various principles in which they work in. And the reason for that session was that before we attempt any anchor design, it's important to understand the principles of post-install anchors in order to have the data available so we can begin a design. Then part 2, if you go to the next slide, Fethi, was where we actually looked at a design. And the reason we felt this topic was very important to bring to you as an engineering community was that we had a new anchor code published in South Africa in March 2021. This code was a direct adoption of Eurocode 2 Part 4, which is the European code for fastenings for use in concrete. The SABS implemented it as is, and it's known in South Africa as SANS 51192-4. So part 2 of the session was basically dissecting this code. I hope most of you on the call who's joined have got yourself a copy of it, but in this 300 or 200 page document, lots of information. Part 2 was basically us trying to condense that information to make it digestible for you as a community. We went through various failure modes of anchors and various other topics that's linked to the correct design of anchors now in South Africa in accordance to the code. Now, I mentioned this a little earlier. Foundation is important, and understanding anchors and the principles of them is critical before we even start the design. This is a slide that I've shared in the last 2 sessions. I think it really simplifies what we need before we enter any anchor design. The first thing is a design method. As we mentioned, we've got the Eurocode 2 Part 4, or SANS 5111992-4, as a design methodology that we can all use. Together with that, you'll need anchor technical data, which is based on an ETA. So the ETA is a third-party organization that does technical testing on our anchors in line with Eurocode 2 Part 4. You have to have this in order to do an anchor design. And then from your side as engineers, you will need your loads. So any sort of actions and reactions acting at the connection, you will need to define those, and together you can do an anchor design. Now, there was one element that we omitted from the last session that we're going to bring to you in this session that's super critical. This is at times a gray area. This is at times a vague area, but it's very clear in the code, and Fetty will take you through that there's more to anchor design than just the anchors itself. And that's why the name of this course is Advanced Connection Design. The connection is not purely made up of the anchor. It's a combination of the anchor and the steel element that you're fixing into the concrete. And without giving too much away, we're going to talk about connections today in its holistic form. The anchor, the steel element, which we speak about as a base plate, and you won't have to listen to me too much. I've done the last 2 sessions. Fetty's actually going to be the one that's going to be presenting this topic. Just to set the stage for him, and not to blow too much smoke here, but he was one of the key global members of Hilti that drove this topic locally and helped launch the topic of connection design in South Africa. So he's actually the best person to be presenting it to you. So with that, and not giving too much away, I'm going to hand over to Fetty, and he will take you through part 3 of Advanced Connection Design. Thanks.
All right, thanks, Mike. I hope everybody can hear me right and well. Rushan, please let me know if my voice is bad at any point. So, I mean, again, like a quick introduction, as Rushan said, I'm the Regional Technical Marketing Manager, practically responsible from the technical products of Hilti in our region, which consists of Middle East, Turkey, and Africa. So I've been with Hilti for 5 years, and in my current position in Dubai for 3 years. So I'll just give you a brief presentation overview. So the purpose of this presentation is to, highlight, just give me a second, let me do some arrangements with my screen. Okay. The purpose of this presentation is to highlight and explain 2 different methodologies for baseplate design and analysis. We start by answering the simple questions: why do we need baseplates? We then briefly look at how the externally applied forces are transferred to anchors in the absence of baseplate design checks. This is the case where the baseplate is not part of the load path that leads us to our first type of baseplate design methodology based on Eurocode 2. Right now we're talking, but again, it's kind of quite similar if you have ever compared the main 2 codes that we have in the world, which is the American code and the second one is the Eurocode, right? They are both quite similar when it comes to explaining these kind of details on anchor design or any other stuff in construction. So Then we dive into the details of this method a little bit, look at assumptions that help simplify the design and analysis of baseplate using this method. Let me check. Oh, okay. By the way, excuse me, I forgot to change the naming here. You can see in the screen it says ASC Design Guide 1. Sorry, it's quite similar as I said. Let me bring my laser pointer. So this should be Eurocode. Apologies on that one. So don't get discouraged. We will be mainly talking about steel design of the base plates or steel element of the base plate. So not too relevant. Again, this helps us, as I was saying, this helps us the transition to the second type of baseplate design methodology, which is the main thing that I want to talk to you with today, which is the finite element analysis. We start with some nomenclatures and talk about some limitations of a nonlinear plate behavior. This takes us to a quick brush up of the fundamentals of finite element analysis and leads into component-based finite element analysis. Here we talk in detail about the parameters that define a non-rigid base plate, and how to interpret the results of FEA. I will start to mention it as FEA instead of finite element analysis all the time. So FEA baseplate analysis. This session ends with a few non-rigid baseplate design examples using FEA through our software. Right. By the way, I'll just stop sharing the video just in case that I'm using too much bandwidth. All right, again, as I said, this is our agenda. So we start, I'll start off by discussing the reason of why we need a base plate shortly. After that, we will look at the current base plate calculations using Anchor design software. Again, don't get confused about the DJ. We call it DG1, the design guide 1. I'll be talking about the Eurocode part mostly, and then we end with finite element analysis. Okay, so why do we need, or what is the purpose of a base plate? So base plate completes the load path. That's one thing. I mean, it usually can get overlooked in many scenarios because I've heard the terms of, I mean, it's just an anchor anyhow, right? Like it just like holds a place, but actually it's not. I mean, it literally is a node that you need to calculate in all of your calculations, right? To transfer your loads again. So as we all know that a load path is fundamental for proper design of any structure and base plate, which is a piece of this load path, and then the base plate is a piece of this load path. It provides an even and smooth transition of the load from steel to concrete. Typically, the base plates are the same shape as the foundation. Since most foundations like spread footings and piers are rectangular, most base plates are again squares or rectangles, which helps in spreading the load into concrete. This is also evident from both Eurocode and American codes, which includes the area calculations of both a base plate itself and then the concrete, and then you just make a simple calculation out of it to understand the stress that you're putting onto your main material, which is the concrete. And again, just imagine what would happen in the absence of base plates. We will be transferring point loads into the concrete, which depending on the magnitude could cause a punching effect and damage the concrete, right? So analysis of a base plate is very similar to beams. Think of base plates as beams in 3D. Like beams, base plates are also designed for their flexure capacity, and the design process is very similar. The thickness of the base plate is the most important design parameter, along with its length and width. We typically increase the thickness of base plates to avoid using stiffeners. Okay, now I'll go into a little bit on the current base plate calculations using Anchor design softwares, like this can be any. If you're with us for a long time, you know that we had Profis Anchor software. Now it's again within the Profis Engineering. It's an Anchor design software, but we can also do the base plate design. So generally speaking, the current Anchor design software in both South African market or Middle East market, or in Europe market, or US/Canadian markets, that also uses the Eurocodes and American codes from time to time, use the strain compatibility method. So as you can see on the point number 2, So they use strain compatibility method to distribute the applied forces and moments to anchors based on the based on the assumption that the base plate will be appropriately designed, so it can be treated as rigid. The base plate in this software is not part of the load path, and so it does not resist any loads coming from the column. As a result, more loads go to the anchors. These software use strain compatibility, or in another term, triangular stress and strain distribution, to calculate the tension and compression loads being transferred through the base plate. This can result in an over-design of anchorage and may provide a conservative solution. And since the base plate is not evaluated by the software, it must be independently analyzed to verify compliance with any model steel design codes. The only model codes and standards that are used by the software are the concrete design codes for design of anchorage, governed by Eurocode 2 if you're doing a Eurocode design, again ACI if you're doing an American design. So why design rigid base plates, right? Just a moment. So we design base plate because basically the regulation tells us to design rigid base plates based on the concrete capacity method. Assuming a rigid base plate is okay, completely okay, but this assumption must be verified, which we will cover in the upcoming section. Assuming a rigid base plate and not verifying the assumption can lead to underestimation of loads, which you would guess is unsafe. For example, as an example, you can see the Eurocode 1992-4 or Eurocode 2-4 section 6.2.4's guidance on the base plate calculation. Here, as you can say, the assumption, this is an assumption made by Eurocode, and it says like if the requirement for the deformation is not fulfilled, the elastic deformation behavior of the fixture shall be taken into account adequately to determine the design value of tension loads acting on each fastener. So again, I mean, it's always going back to, it's always trying to go back to the rigid assumption. I mean, rigidity is always an assumption. So this is what I'm trying to basically tell you. Yes, the code tells us to design base plates rigidly, right? Yes, we want our base plates and our structure as rigid as possible and as strong as possible. However, the reality doesn't reflect the theory. So what happens when we design or assume the rigid base plate design in our calculations, when we go to the field or when we go to like real life applications, what we see is like deflections, again strains, too much strains and too much deformations on steel plates, etc., plates, profiles, or stiffeners, anything that you can put on your base plate. So again, as an assumption, yes, it makes sense to have this assumption. Yes, it makes sense to design as rigid as possible, but how would you understand if your base plate is 100% rigid or not, right? So I'll go into the finite element analysis method and explain you how or what are the differences when we are talking about the finite element analysis based non-rigid solution. And then we will do an example on the base plate. So Eurocode 2 methodology based on rigid assumption, and also same with, again, AASC Design Guide 1 methodology based on rigid assumption is theoretical and generally conservative. It is also code compliant, so that's for sure. However, the behavior of base plates under externally applied loads in reality is dependent on loading, profile, concrete type material of the plates, concrete type of material of the base plates, and numerous other factors. So for this reason, base plates in reality generally don't bend only about fixed bending lines. Bending generally occur based on the load distribution. So this non-rigid behavior cannot be explained using Eurocode 2-4 or AASC Design Guide 1 based on rigid assumptions. Again, please note that I'm always trying to emphasize on the word assumption, right? So just keep that in mind. This is where finite element methodology is used to capture the realistic plate behavior. Until now, until now. So whatever I said about rigid assumption, we were always on the left-hand side, right? Or left-hand side world. And what happens in this world? In this world, everything remains. If you remember the 3 words that you usually hear in every book or in every structural piece that you read when you're talking about the base plates and strength compatibility, it's rigid, elastic, and linear. So base plates remain rigid, the behavior is linear, and it follows the linear elastic curve of your stress strain graph. But remember, all the assumptions I've discussed with you so far, like, is it realistic to you? Really not. Like, in reality, your base plate has a tendency to do an uplift, right? Like you are seeing on the left, the right-hand side. In reality, design of the base plate is highly influenced by what kind of loads are applied, what is the material of your profile, what's the rigidity of each different thing that you have in the base plate. What's the stiffness of the material? So stiffness is also a really big factor and differentiating factor in every material. All comes in handy when you want to look at realistically how a base plate behaves, and all this stuff makes the behavior non-linear. Now we will start talking. We will start to talk about how we handle this behavior. What are some of the applications that might be affected, for example? So here are some possible non-rigid base plates that we just highlighted as example. You know, like, there are certain applications where a rigid base plate assumption generally does not hold. These are cases where the base plate is thin enough and will not behave linearly under expected externally applied loads. Again, here are the examples. So number 1 is a ledger angle type connection, which we quite often see everywhere we go, in every kind of construction or in every kind of building type, right? The second is, for example, we said Hilti MQ base plates. So these are our installation systems. We recently changed these to naming to empty, but doesn't matter. I mean, installation systems, or we call them again modular support systems, and so, you know, like, this is approximately 4 millimeters thick, and like, if your material, if your base plate is 4 millimeter thick, just like think about it, 4 millimeters, how small it is, would you really call this a rigid steel structure or rigid base plate if when you apply really big loads on it? I wouldn't. Again, the third one is that the plates used in some special, you know, like seismic supports, like non-structural components, as you can see on the right-hand side, it can be canopies, or it can be, again, in many mechanical and electrical applications like piping supports or cable tray supports, etc. You can see this seismic, again, the seismic part to resist the seismic loads. Again, these are all really thin materials, and it's really tough to call these materials or these base plates rigid. I mean, when you do an anchor design on any of these, or these are like just examples, I mean, there are many cases. It doesn't have to be always thin. I mean, thin, again, thinness or the concept of thin is based on the loads that you're applying on your base plate, right? So 4 millimeters can be thin for, I don't know, like 1 ton of a tension force, but again, 40 millimeters can be thin for, I don't know, like 100 tons of tension. I'm just making the numbers up, but you understand what I mean from the examples. Again, these are all examples where a rigid assumption may not predict the true behavior of the base plates under applied loads. Here is where finite element methodology based base plate design checks will yield a more realistic behavior. There is no textbook definition of when to consider a base plate rigid and when to use a non-rigid approach. So this is where the experience of the user comes in handy. An experienced engineer is more likely to be a better judge of whether to use the rigid or versus the non-rigid base plate design approach. So before we deep dive into the details of nonlinear base plate analysis using FEM or FEA, it is imperative that we look into some of the consequences using the non-rigid assumption. One major consequence comes is the lack of model code compliance. Okay, let's understand this. Eurocodes or US steel design model codes based on ASC allow the user allow the use of nonlinear or non-rigid methods for designing base plates in order to obtain the forces on the anchors. So base plate is part of the load path, and force distribution takes place using finite element analysis to the anchors. Once we have the forces on the anchors, determined, the second step is designing the anchorage system in accordance with Eurocode 2-4, right? Here is where we see a major shortcoming of, or again, ACI 318 doesn't matter. Here is where we see a major shortcoming of the nonlinear assumption, as the both Eurocode and ACI 318 anchoring to concrete provisions require the assumption of a rigid base plate in order to perform anchorage design per, again, Eurocode or ACI. Excessive deflection in structures may also be a consequence of a non-rigid base plate assumption. So for structures where the design is governed by deflection, non-rigid base plate assumption must be giving a second thought. So some of you will be thinking that, okay, I mean, I can't use Eurocode 2, I can't use ACI 318 checks. Why am I listening to a non-rigid base plate topic here, right? And the answer to that is that in the software that we are showing here today, or we will be showing here today, the finite element method is there to help you to make an engineering judgment on whether you can use your non-rigid anchor forces to do Eurocode 2 or ACI 318 checks or not, looking at certain criteria, which I will be talking about. But first, understand that this is one of the consequences, right? And this is something that we really need to watch out for, even before, you know, like starting our design. And the second thing is again very obvious. I think is the serviceability deflection, which I mean deflection. So anytime you have yielding, this basically is a sign of release of energy in a structure that can lead to some excessive deflection by default. So be aware of that and make sure that you have that on your mind before even you start to the design. And before I move a little bit forward, I'll just show you a couple of the design verifications in process engineering. Again, we do for the Eurocode. Again, as you can see, I'm talking both about the ACI or Eurocode or AASC or again Eurocode 3. Like, doesn't matter which code that we are talking, because they are practically preaching for the same thing. They are practically telling us to do the same thing. Assume the base plate rigid or make a rigid base plate, but they don't tell us how to calculate the realistic scenarios where we face in reality. So before I go forward, like just to refresh your mind and give you some idea on what do we use within the software as well. So for profile and stiffeners, we use Eurocode 3 and this relative section for von Mises stress. For limit strain, we use again in 1993, again, relevant sections. For base plates, again, we use Eurocode 3, as you can see, Eurocode 3 all the way. And for anchors, as you know, as per, we use the anchor failure modes as per the new Eurocode 2-4, or the naming might be different within South Africa, but again, it's the same code. For welds, again, we use, as you can see, Eurocode 3. And for concrete, what we use is Eurocode 3 and a mix with Eurocode 2 part 1, which gives us the loads. So again, first, now I'll go a little bit deeper into the topic, but let's start with the graphical representation of Eurocode 2 philosophy as far as baseplate design is concerned. There is again like some terminology which I just mentioned earlier, but again there is some terminology here which is used interchangeably but means one and the same thing. For example, elastic and linear are the same in the context of behavior of the material, and elastic behavior is graphically represented by the linear portion, as you can see here in the graph. And again, elastic and linear are the same. And elastic behavior is graphically represented by the linear portion of the stress strain curve. Base plates that behave elastically are also referred as rigid because there is no physical change in their profiles. They can tilt under an externally applied moment, but they don't bend. The profile is linear, rigid, and behavior is elastic. Again, please note that the context of elastic behavior is in relation to like the linear section of the stress strain curve as it applies to the behavior of base plates under applied loads. In the civil or structural construction world, in the world of, again, mechanical engineers, the word elastic refers to a material that can flex. However, in the construction industry, a rigid base plate showing elastic behavior is not flexible. By far, a bigger consequence of non-rigid base plate assumption is the fact that anchor forces are more realistic than if a rigid base plate was assumed. They can be higher than the anchor forces out of a rigid base plate assumption. So let's look at the two, let's say like two most common loading conditions, right? In the case of pure tension, which you see on the left-hand side, in the case of pure tension, a non-rigid base plate has a tendency to deform and curve upwards, as shown in the slide, as shown here. This change in the profile induces forces at the edges where the steel interfaces with the concrete. These are called prying forces. These prying forces contribute in an overall increase in the forces on the anchors. This can easily be seen by summing the forces in the vertical direction, again, in the second free body diagram on the slide. So the forces, the different forces here that I mentioned. The second very common case is the one of the applied moment. Again, this is the right-hand side. Let's see how a non-rigid plate assumption in this case leads to an increased anchor forces. In the third free body diagram, we see a rigid plate under a moment loading. The plate is tilted under the applied load, but the profile remains intact as it is rigid. Notice the moment arm, right, Z, between the anchor location and the resultant compression, which is assumed to be at the point where plate makes contact with concrete. Now, notice the change in the length, right, in the length of the same moment arm when a similar moment load is applied on the same fixture with a non-rigid plate. The moment arm that red reduced is less than Z. This reduction in moment arm is due to the fact that a non-rigid base plate bends and makes contact with concrete at certain locations along its profile, unlike the rigid base plate, which does at the end. This causes a reduction in the lever arm length, right? Now, by summing the forces and moments about by any point in the free body diagram 4, it can be seen that the tension forces actually increase due to a smaller bending arm as a result of non-rigid profile and non-linear plate behavior. I think, I hope that everybody is clear on this one. I mean, again, same thing for the tension. Basically, these prying forces are also added. So these cause extra forces on the anchors. And for the moment, I mean, it's I think like again, same thing. Force multiplied by the moment arm equals our moment, right? So if you have less moment arm, then we have to have more force on the anchors. So now, before I go into the very details or each and every detail of the component-based finite element methodology, let's look at some terminology in regards to rigid and non-rigid base plates that are often confused. For the rigid case, which is the one on the top, For the rigid case, the terms elastic, linear, and rigid all relate to the same, as explained earlier, behavior of the plate, which is well represented by the linear portion of the stress-strain curve, as highlighted in yellow. Such a behavior is easier to analyze using Eurocode or Design Guide 1 methodology, and the ease of calculation is due to various assumptions, as explained earlier. Now, let's look at the equivalent terminology for a non-rigid plate. Elastic becomes inelastic, because the behavior now follows the stress-strain curve beyond the yield, right? Now we are in this section of our stress-strain curve. The base plate behavior may be nonlinear under some loading conditions also. Nonlinear behavior generally requires advanced computation methods to analyze. As far as the profile of the plate itself, we can see from the free body diagrams that the white plate deforms under the applied loads and does not maintain its profile. Now, okay, so we have gone through the definitions, the terminology, the differences, etc. Right? Now comes the million dollar question. How do I go about analyzing and understanding base plate's behavior? That's where the real engineering comes into play. Unlike the first method, or unlike the rigid method that I mentioned, we cannot use simplistic approach because there are no assumptions, and because this is a real behavior, right? So in order to understand this behavior, we have to use numerical methods and advanced analysis. Easiest and most common computational method for analyzing non-rigid plate behavior is finite element analysis, or FEA or FEM. Because as seen earlier, non-rigid behavior is generally not analyzed using simple matrix algebra. Consider a simple plate structure with uniformly distributed loads, right? Like on this one. The objective is to find the reactions at the fixed boundary. As a first step, we discretize the structure in elements, in this case, squares, like these small elements. The load is transferred to boundary via the nodes and elements. So whatever load that we're getting, it's going through each and every node, right? Like we do in the whole of the structure as well. Each element is connected to others via nodes, and the force and deflection transfer takes place at the nodes only. The more we discretize, or in other terms, break the plate down into smaller squares, the more accurate the reactions will be. Reactions and results at the fixed boundary are obtained in terms of deflection, force, strain, and stress. It should be realized that the more the structure is discretized, the more challenging and laborious the analysis becomes. And there comes a point which hand calculations cannot be performed, and a computer program is required to do the analysis. I mean, maybe, yes, you can calculate 10 or 20 calculations on a plate, but then when you make the rectangles or whatever the shape is smaller, and then you have 100 of them for just one plate, it just becomes impossible to do anything at all, right? So let me continue. We discretize the elements and then we connect them at the nodes. Then very importantly, we define a behavior of these elements, and that behavior depends on the material of these elements. Material, the engineering properties of the material, play a really big role in finite elements in making sure we obtain the realistic load transfer. So your modules of elasticity, your moment of inertia, your section modulus are all part of determining the stiffness of these elements. Once that is in the picture, you have a more realistic material behavior as far as load transfer is considered. The other thing is that the results are obtained in the form of stress and strain. The more you discretize, the better your results are. What does that mean? That means that very, very quickly hand calculation doesn't help you anymore. Your math becomes so complex that you need an equation solver or a computer program, and I'll show you why. Now, let's look at some basic elements. Discretization of structure is the key to any FEA or FEM. A structure can be discretized using different types of elements. There are like 1D elements that are used for the load analysis in most structure analysis programs. Then for 2D modeling, the most common types of elements are 2D elements or plates or as we call them, shell elements. 3D elements are mostly used for more complex machine design type applications, as far as I know. You can correct me if I'm wrong. Again, like the 1D elements are typically what most structural engineers like me and like you and like most of you you use in our everyday like RISA, Procon, I think, as well, STAR, or those programs where we have to do a load analysis, right? Some people do a little bit more sophisticated structural design. They use 2D elements, which are shell or plate elements, again, and which are also called 4-node elements. And then we have the 3D elements, which are used for more sophisticated machine design type of studies that are mostly undertaken by mechanical engineers, again, as far as I know. Just please let me take a quick sip from my water. Right, thank you, and apologies for that. Talking continuously makes you thirsty, apparently. All right. So FEA or FEM methodology is based on the stiffness of the material. This is what can make it more realistic than general hand analysis, because the engineering and mechanical properties of the material that make up its load transfer abilities are accounted for in the stiffness of the material. This methodology is based on matrix algebra. The governing equation is so this governing equation is F, which is the force, and K is the distance or the distance that we have, and where K is the K is the stiffness matrix, and X is the displacement matrix as a result of forces created within the element caused by displacements. So these displacements are the degrees of freedom at each node, as shown in the example of a triangular element. So here's an example of discretization, and I hope I'm, yeah, as far as I know, it's called discretization, but again, you can just correct me if I'm saying that word wrong. Again, sorry, not my native language, English. So in this 2D examples, or in this 2D example, the 2D plate or shell elements are used. It should be noted that there is a larger concentration of elements where the curvature is changing. So 4 nodes are used on the longer and you know, straighter sides, where the whereas triangular elements are used at the change in curvature. So this is a commonly used technique to capture the appropriate or correct or exact load transfer that goes through this curve. So let me talk about the difference between what we have or what we use in our software as well. Again, it's the same thing, but it's more advanced. So traditional FEA or traditional FEM is used for load analysis in everyday structural analysis using 1D elements, right? The accuracy in load transfer is due to the inclusion of the stiffness of the load carrying members. So these are beams and columns in the analysis. From the load carrying members, the load is transferred into the connection. Right, in a traditional FEA setup, the connections are detailed separately in a spreadsheet or a separate application. This is where component-based finite element analysis or finite element method provides a built-in method to evaluate the connections. No separate hand calculations or extra analysis or a second software is required. So I can very simplistically explain to you that what that means by using something that we all do as structural engineers in our everyday life, and that is the frame analysis, right? I mean, I was doing these, but like it's been kind of years for me that I haven't done this, but you are probably doing these on a daily basis. So here's a simple frame with a simple frame loading on it. So with a simple loading on it, continuous. And most of us have done this many times across our careers. And what do we do here? Well, we look at how the load is transferred from where it's applied and all the way to the foundation using these beams and columns, where the load is transferred using the stiffness of the member, right? That's where finite element comes into play. And that's where the stiffness matrix comes into play. First, what happens? Load is transferred from the member to the node number 4, let's say, to this side. That's the connection between a beam and column. What's present over there? So at a beam and column interface, we typically have a connection. This can be a welded connection. This can be a bolted connection, right? In old school finite element, what I remember people doing is when you have to analyze this connection, you take the forces at the node number 4, you go on a separate spreadsheet or a program or hand calc, and you compare those loads against a stiffness or a strength of a certain connection, which has been calculated separately, right? So you are going in and out of the software. In component-based finite element, you don't have to go out of the software, because once you go to the node number 4, like I'm right now, as you can see on my cursor, if I click on node number 4, the different options of the connections are built into the software. And let's say I have 4 types of connections that give me 4 options based on what connection I click in the software. A spring is activated. A spring is taking the place of resistance value of a connection. Okay, so I'll explain in the upcoming slide as well. So the spring constant there means a certain value, resistance value. And that's how the software in one shot automatically checks that capacity against the load applied, and it tells you it works or it doesn't work. So you don't really have to go outside of the software. This is called component-based, and spring is a component, and the whole structure is built as different components all working together. This is the concept that we will use to study how process engineering handles the base plate connections in finite elements. I mean, what you see in the software, if you have seen it before, is quite simplistic. It just happens within a couple of clicks, but this is all the background that is happening, and this is what I'm trying to explain to you, the theory of it. So again, now I'll explain the different parts that we have in the base plate. So base plate is a special type of connection where component-based FEM provides added value in the simplification of the analysis of the connection. The column profiles and the base plates are modeled as 2D or shell or plate elements. All other interfaces are modeled as components. Concrete is modeled as you can see here, concrete is modeled as compression-only springs. Anchors are the red ones. Anchors are modeled as the tension-only spring. The welds between the steel section and the plate are modeled as a special plate element with stiffness adjusted to emulate the load transfer through the welds. So let's take a detailed look at the steel in the connection. This applies to the steel section and the plate. These are modeled as shell elements. In finite element analysis, we also define the material and behavior of the elements. In this case, the behavior is based on von Mises yield criterion. An example, material behaves elastic before reaching yield is what I'm talking here. So the regular graphs that you know. This behavior is depicted by a bilinear stress strain curve as shown in the slide in green ink. the material behavior follows this curve. So the behavior is linear until Fy or yield, which is the classical behavior under von Mises yield criterion, and thereafter, if the load further increases, the material follows the horizontal section of the curve and starts to have plastic and permanent deformation in the structure, which is captured by a plastic strain limit. In example, let's say strain hardening. The user can control the material behavior by controlling and limiting the plastic strain limit. So in the model US design codes, there is no such provision. However, Eurocode suggests a 5% plastic strain limit.
Fethi.
Yeah.
Hi, sorry. I'm not sure if it's just me, but I seem to have lost your screen.
Oh, really?
Can everybody else see it? I hope it's just me. Debbie?
I see it. I'm good.
I can
Okay, cool.
see everything.
Good.
Thanks.
Yeah.
Sorry, guys. All right, cool.
No
Continue,
problem.
man.
Thank you. I didn't even notice that.
Go for
I
it.
don't know how it happened. Sorry.
No, it's good.
No.
It's good on my side. So
Okay.
Good. Go for it, man.
Yeah.
Cheers.
Okay, cool. I mean, which slide are we? Did you lost me?
It's okay, Fethi. Continue. I think all the delegates can see you have seen their comments now. I think there's an issue on my side. Okay.
Okay, no problem. We'll just tell Hilti to provide us better PCs. All good.
This is recorded. I'll make sure to strip that part out and take it to my boss.
Yeah, all good. Again, so let me go a couple of. Okay, just give me a second to recollect my thoughts. Okay, what were we saying? So I was mentioning that the user can control the behavior of the material to control and limit plastic strain limit. Yeah, we were talking about the plastic and strain. So in the model United States design code, there's no like a provision as such that you need to limit your plastic strain. But in Eurocode and in Eurocode, it is suggested to have at least or at most like 5% plastic strain limit. Again, this is just a suggestion. You don't have to go with that. You can go with any limit that you feel is right based on your own expertise. I mean, you can say that I've been modeling and calculating this for over 20-30 years, and then it's not 5%, it's 4%. So it's again up to the user, and it's again up to the engineer, as is everything, right? All right, second important part. Okay, let me check the chat. Okay, everybody can see it. Awesome. Thank you very much. So second important part is the anchors. Because from the plate, the load transfers through anchors. And how is that done? Anchors are modeled as I said like before, and as you can read here, anchors are modeled as tension-only springs. So under a tensile or bending load, this non-rigid base plate yields and permanently deforms due to the distribution of the forces based on the stiffness of the plate elements. The loading adjusted or to account for this plate deformation causes an uplift, as you can see, or as you remember from the previous slides as well, or as you can see here, it causes an uplift and causes the spring to elongate by an amount of X. The designer chooses a certain anchor, and the stiffness of that anchor, which was K, is associated with the spring. The product of the anchor stiffness activated as the user chooses an anchor, and the measured spring displacement is used to calculate the tensile forces transferred to the anchors. Again, remember the formula, right? That we discussed in the previous slides. F equals K multiplied with X. Again, X is the elongation on the anchor spring and or tension spring, let's say, and K is the stiffness of the anchor. Again, here you have to be really specific on this coefficient especially. So basically every anchor has a different stiffness factor. So this is really important, by the way, even to do every kind of calculation like this. Every anchor has its own stiffness value. Even like you might be familiar with a couple of our anchors. even within the same anchor family, whatever we name it, doesn't matter. A different size of an anchor can have a bit of a different stiffness value due to, even I don't remember how to comprehend, but yeah, I mean, just know that every anchor has a different stiffness value. So that's why these are really tough calculations to do by hand. That's what I was trying to say at the end. All right, now let's look at the third element, which is very vital, and that is concrete. So every time your base plate is in touch with the concrete, there's always bearing and there's always a deformation of the concrete as well. Concrete is modeled as compression only spring. The stiffness, the K of the concrete, is defined by the modulus of elasticity of the concrete and the effective height of the subsoil model using the complex formula on the slide, as you can see. So this is the formula that we use to calculate the stiffness of whatever concrete member that we're using. The complexity comes from concrete being a non-homogeneous material, as steel is. And this complex numerical model by Winkler and that is used by this program to depict the deformation of the concrete. Once that deformation is calculated, it is depicted in the graphic user interface by these compression only springs, the gray ones that you see. Again, this is also done by using the Winkler method. If you're curious about it, you can check it out. The stiffness, or the K of the concrete block, that comes out of the Winkler method, also which is basically shown by this equation. And if you notice, this equation is also a factor of E sub C, as you can see here. So which is the modulus of elasticity of the concrete. Basically, concrete properties, just like the steel, are used to determine the stiffness of the concrete, which is your classical finite element approach. Now, the other part is welds, right? The welds are also behaving as plate elements. Their density are a little different from that of the plate or the column, and their behavior is along the lines of a bilinear stress strain curve. The welds are modeled as deformation constraints. This is a connection between two plate elements on the column side and the other on the plate side. These nodes are not connected directly. However, a midline surface of the connected plates is modeled with an offset. This offset represents the weld configuration and the throat size of a fillet weld. Based on the node displacement distribution of the connected plate, stresses are calculated in the throat. All right, so here are some examples of the welds. The user has the choice of placing the welds under any segment of the steel section, like be it under the web or the two flanges, etc., or custom or stiffness welds, etc., or custom stiffeners, again, anywhere you want. In case fillet welds are not sufficient in strength, an option of full pan, or in other words, it's called butt welds, is also available in the software. So I think like this was the last member or last thing that I want to mention on this one, is that it's meshing. All the finite element components and the attached members are held in place by a process called meshing. The process of meshing helps ensure the plate elements are properly connected at the nodes. If you remember the one of the very first slides that I explained this, and all the components are rightly placed where they should be as per the model. The FEM or FEA program will automatically optimize the design by choosing the most appropriate mesh setting for you. So, but again, you have the option to go in and change the mesh settings if you want. But again, our recommendation is to stick to what's in the program, which is again gives you the most optimized design anyhow. So once the forces on the anchors are calculated, and as a second step, the anchorage design is to be performed, it must be understood that Eurocode 2 or ACI 318 provisions assume a rigid plate, right? This is what I said in the beginning. However, the finite element analysis on anchor forces, as established earlier, are based on a non-rigid plate. Therefore, the user has to use his or her engineering judgment and experience in anchorage design to decide whether it is okay to go ahead with the non-rigid plate-based anchor forces. The software helps the user in making this decision by providing equivalent rigid anchor forces that were to be obtained from a rigid plate assumption. I'll show you an example and you will clearly understand what I mean on this one. This is accomplished by making the modulus of elasticity infinitely large when calculating anchor forces using a non-rigid base plate FEA methodology. The idea is that by comparing the non-rigid plate anchor forces to the rigid plate forces, the user can decide if he or she can pursue with anchor design using non-rigid forces or revert back to the design and make some changes. For example, if the non-rigid plate anchor forces are in a, let's say, close proximity to the ones from a rigid assumption, the user will most likely go ahead and use the non-rigid plate forces to design anchorage. Here also the presence of prying forces in the analysis can help the user validate the increase in the non-rigid plate anchor forces. Along with a set of equivalent rigid plate anchor forces, the user also has two very important parameters that can be very helpful in concluding if the resulting finite element analysis anchor forces should be used for Eurocode or ACI model code checks or not. These are, number one is the plastic strain percentage and the amount of plastic deformation. All these parameters can help an experienced user to decide quickly on whether it is okay to go ahead and use the non-rigid plate-based anchor forces for Eurocode or ACI checks or not. And the last thing before I go to the example is explaining you a little bit more about plastic strain limit. The plastic strain limit and deformation, along with the equivalent rigid anchor forces, are the key parameters in deciding whether to continue with anchorage design given the finite element analysis based anchor forces or not. The behavior of the steel is based on a bilinear, again, as I said, like stress curve, as you can see in the green. So remember that Eurocode limits gives us a limit of 5%, but the AASC doesn't give us, or ACI doesn't give us any limit on this one. So these are all, again, recommendations, assumptions. So it's again on up to the user to use these limitations, etc., that we also put in our software as well. So I hope it was clear. I tried to go through as you know, like point by point to and word by word explaining all these. I know these are really, you know, like for some it's heavy topics, etc. But let me take you through the software and show you what I mean from the previous slide, the comparison, or being able to see the rigid and the non-rigid forces applied and the differences in between. All right, so now let's open a Profis Engineering. Okay, so for those who don't know, it's profisengineering.hilti.com. Same anywhere globally. You enter this and then you come to our software. If you haven't tried it before, it will ask you a registration, and then you can have a 30-day trial. If you enroll to the 30-day trial, please just let Rishan know that you need help and you need some guidance, and Rishan and his team of amazing people will definitely come out and help you out. Okay, so we went through the software in the previous section as well, but let me take you to a random design that I'll make now. It's just an like example just for the showing the software purposes. I'll just try to do an example where I can show you the difference that I just told you. Okay, it asks me if I want to use advanced anchor plate design license. Yep. All right, so this is what we have. I don't even know, like random stuff that we have. I'll just put a couple of different forces. Push the tad bit. Okay, let's do it like this. Okay, our concrete is C25. I'm using apparently an HST3 anchor, which is a mechanical anchor. Here you can see, all good. What else? What else I need? I'm checking my details. Okay, concrete, all good. 250. Let's make this 400. Supplementary reinforcement. I'm not going to go into this one. Yep, square or rectangular plate. Let's check for 2x2. All good. My profile is IPE 200. Material is S235. Doesn't matter. I have my welds. I have my butt welds. Let me also show you the stiffener part. So, okay, this probably doesn't work. Okay, this sort of works. Let's say that we put these welds, and then I select fillet welds for these stiffeners. Makes sense. And here I select my component-based finite element method that I mentioned to you. As you can see, my design method is selected as Eurocode 2-4, and I hit calculate. Even during calculation, you can see that the software is doing an iteration for rigid and one for component-based or CBFEM. Okay, so this is the main thing that I was mentioning you in the last sections of the presentation. So in regular anchor software, right, even like within our software as well, if you're using the free version, etc. So basically that's an anchor design software, but here what we offer is the base plate design software. So what's the difference? So as you can see, this is equivalent rigid anchor plate. When you hover over, it will also give you explanations. And this is component-based finite element method of the anchor plate. So if we were to assume this base plate rigid, if we went with the rigid assumption, our anchor forces would be on anchor 1 and 3. So these two anchors, 3.7 kilonewtons, and other anchors are 0. Okay, do I have any plate deformation? That's 0 because I'm not calculating the base plate. But when you see in reality, what happens to this base plate is that under these applied forces and under the, changing shape of the base plate or the profile, our actual anchor forces are, for anchor 1 is 5.15, for anchor 2 it's 0.4, for anchor 3 it's 5.5, and for anchor 4 again it's 0.3, and I have a anchor plate deformation of 0.1 millimeter. You can see, for example, this is just an example, but in this example, even like I just made it up, in this example, you can see a 49% difference on my anchor forces from the first to second. Can't this anchor carry this force? Yes, probably, but still, you can see the big differences that you can have when you're assuming, when you have a rigid assumption. I'll just hit confirm. The software also tells you that be aware that you accepted a 49% difference in your anchor forces, etc. So it always gives you the notification and then the warning about that one. So also like seeing the deformations or being able to understand where our plate is being mostly, where this basically shows us where to focus, like in your design softwares as well. So you can see the difference. So let me create a report as well, and then I'll take you through the report quickly. Okay, let's open this up. Let me come a little closer. You can so you can see easier. Okay, so it gives the regular anchor design data that any anchor design software gives you. It's all good. I'm going down. Again, loads on resulting anchor forces. My anchor reactions here, as you can see, it's kind of same. It's just like rounded up to 5.5, but this is the actual one. I'm going down. Gives me my tension load, steel strength, pull-out strength, concrete cone breakout, etc. All the regular stuff that we know about anchor designs. Now let me go down and show you some of the differences that we have. Okay. Okay, so practically in usually in our old anchor software or in our like standard free of charge version, this is where you will this is where your report will end. So at page 10, where you have the drilling and installation instructions and you know, like recommended accessories or installation data of this design. But what happens is that since we are using the component-based finite element methods, you will start to see the anchor plate design and all the inputs and all the data that we put into it. So as you can see here, it tells you your equivalent rigid anchor plate if you were to use a rigid base plate assumption, again with like infinitely large elasticity, modulus of elasticity. It's the same thing as rigid assumption. And as I said as I showed you on the screen, the differences in between, you can see, you know, like equivalent stress and plastic strain of your plate, of your profiles, of your stiffeners, if everything checks out or not. Again, equivalent stresses on your plate and anchors. It gives you the plastic strain calculation. It gives you the whole bearing calculation. Let me go down. We also give you again like whole bearing calculation. It goes down a little bit for each anchor. So it gives you the weld calculation, stiffeners, or to profile or anchor plate. As you can see, every stiffener with how much weld, etc. All the details that you need. And it gives you also your concrete calculations. I mean, just look at how much details it goes into a calculation of component-based finite element method. So it practically becomes 18 or 19 pages of design. Basically in a couple of minutes. So I mean, this is all that I wanted to show. Rishan, if you're there.
Yes. Yes, stay on the screen, Fethi. There were a couple of questions. Sure. I had to pop out and pop back in. So Debbie, you need to maybe help me with some of the unanswered questions. There was a really good one about pin connections. But while you're on the software, there's a couple of software questions. Yeah, Fethi, I left all the difficult questions for you.
Oh, thank you very much, man.
Ahmed Mutala has a question about the software itself. So the first one is, would Profus ever allow the analysis of a solution using anchors in combination with existing HD bolts? I can help you answer that. I know the answer will be no, but
I mean, HD bolts, I'm assuming it's bolted connections that we're talking, right? Steel to steel.
Yeah, so cast in bolts basically.
Oh, okay, awesome. So to be frank, what is the answer that you want to give, Rishan?
So Ahmed's question is more, would the software allow us to do a combination design under one base plate? So a few HD bolts in place, and maybe if the guys misplaced it, a couple of post-install anchors.
Okay, got it.
So it's
okay,
a mix,
so mix of cast in place and post-installed anchors. Okay, yeah, on that one, I'm sorry, but unfortunately it's a no. So it's practically not possible, as far as I know, to calculate it within the same software, because I don't know the exact details, but I remember this question coming before as well, and as far as I know, there is no answer to that one so far, let's say.
Maybe while we're there, then maybe let's touch on the cast-in bolts topic and cast-in bolts on its own. Would that ever be a feature on Profus?
I think by the end of this month we will bring that one, but I need to check my calendar. So by the way, yeah, I mean, we update this software constantly. I don't even know at what version we are in right now. Let me quickly check. So it's basically, we started, I think, with 3.00 or the 3.01. So it's about like 74, 75 updates so far on the software. So we update the software quite frequently, everyone. Yeah, I mean, cast in place anchors is a feature that'll come really, really soon. So it's scheduled for a couple of months now, 1 or 2 months.
That's great news. Ahmed also asked.
Sorry. I didn't notify you on this one earlier as well.
Yeah, exactly. So, well, not so great news because castings are our competitors. We want more post-in stock. Let's put it that way.
Right.
Yeah, cool. Ahmed also asked in terms of importing of information onto the software. So importing a DXF of a base plate or anchor layout into Profus. He asked this because he's involved in some projects where there's custom shaped base plate and anchors can only be in certain positions. So can he import? And maybe adding to that, can people export from the software?
So importing a shape or so importing of the shapes, etc., is not possible, but importing of the loads is possible. So that's one. I mean, you can see we have a couple of programs here. I don't know if you have Procon. We don't have Procon if you're using Procon, so I'm sorry for that one. But like these are the softwares that can be connected to Profus. So that's one. We can import loads, not the shapes. But you can also let me take you to it. Where is it? Where is it really? Okay, sorry. Here it's I'm just literally looking blind. So basically, I come to this. Like I can change the shape to anything that I want, and then I can place the anchors as weirdly as I want, or the profile. You can move the profile. So basically, I mean, of course, like it will give you a lot of errors, etc. But you can design any as far as I know any shape of base plate right now, or at least that I know for certain is that this is the most complex post-installed rebar, post-installed anchor design software out in the market right now still. And no other software, for example, gives you the L-shaped profiles, calculations for CBFEM, or those kind of things. So these different shapes we can calculate. I hope this answers the question.
Yeah, good. Just on the Procon topic, so you can import loads, but you'll have to export it into Excel first, and then import it into the software. So the software has a feature where you can import from Excel. Just in terms of exports, Fethi, so maybe
here
what you just showed us is great.
So maybe like it's just Control-C, Control-V from Excel. That's it.
Yeah. Cool. Just in terms of what you showed us now, so we could model the base plate here, position the anchors. Can we export into other softwares from here, or export into DXF?
DXF is? I think we can. CAD,
yes,
yeah, CAD, yeah. Yes, we can. I mean, we can export to CAD models, etc. We can export to Trimble Connect. We can export this to Revit or Advanced Steel if you're using Revit. Again, like 3D model exports, as you can see. I think this covers a big chunk of the exports that you would need.
Good. Good. There's a question from John here. Is the design based on mass concrete or reinforced concrete? So
awesome question.
Yeah.
So design by what you see is what you get right now. Design based on mass concrete right now, because the provisions are according to mass concrete, not reinforced concrete. But we have the supplementary reinforcement option. For example, let me calculate this in tension supplementary reinforcement. So basically, if you know your reinforcement places and details, you can easily design this with reinforcement in the concrete as well. So this is a great tool to design plinths, etc. All those nasty design connections that we all know with post-installed anchors, or any kind of anchors in that matter.
Very good. Very good.
I don't want to go into all the details because this is like this is on its
another
own.
Topic.
Yeah, this is on its own a webinar which I'll soon post on Ask Hilti. It's like 1 hour, 1.5 hours of explanation, but yes, we can.
Cool. There's a few more questions coming through. Debbie, I don't know how we are for time. Can we go ahead and answer them, some of them?
Yes, absolutely. I think, like another 5 minutes to take us up to 5, if that's okay with you. I can always copy the questions as well and let you have them afterwards.
Yes, please, because I quickly left because I couldn't see Fethi's screen. When I came back, all of the questions disappeared, but we will answer them Let's maybe
Absolutely.
touch on Philip Oosthuizen, and he's asked, is the software for sale? If so, how much and where can I get it? Fetty mentioned that there's...
It is for sale, and it is for a very reasonable price, that I can tell you.
Yes, it's
I
reasonable.
mean, by the way, I'm telling you this because I mean we've done over 2,000 you know, what is it called, questionnaires to our customers around the world, and we just based this on the capabilities of the software compared to the third-party structural softwares like STAAD, etc. And then it's like 1/20th or 1/30th the price of whatever they are. And then we have, you know, like over the years in our region as well, Middle East, Turkey, and Africa, and in every country, we have many examples with our steel and metal contractor customers, specifiers like yours, like you are, shown that the optimization of the base plate. So by the way, that's the topic, that's the main topic. So now you can see that this design is really easy. You can see the effect on the right hand side. Anchor plate is not being, you know, utilized, etc. In many cases where people use, you know, like 15 mm or 20 mm base plates as a thumb rule, or in general, the amount of optimization you get from steel reduction or steel optimization is so high that the price is just irrelevant. The price is basically just goes into all these updates and supporting the developers team or developer team that we have on developing the software better. At the beginning, we didn't have the supplementary reinforcement. We didn't have this smart anchor plate selector, which helps you many things, or this ledger angle. These are all, you know, like, or this like cast in place, which will come soon. These are all upgrades that we are funding basically with the revenue.
Cool. Fetty, there's what you just explained. There's a couple of questions that we can quickly touch on that link to that. Lots of questions about how much the software is. I can give you a quick price. So it's available on hilti.co.za. I'll share a link in the chat. It's a single user license is 3,999 Rand a year. So as Fetty said, very reasonable considering the amount of savings and the visibility it gives you. What I do recommend to everybody is go check out the trial that Fetty mentioned, also available on hilti.co.za. It's a 30-day trial. So what happens after this trial is that you will be asked whether you want to continue with the premium version of the software, which includes what Fetty showed you today, the baseplate module, or the standard version, which, as Fetty showed you in his report, the first 10 pages, which is free, and that's just anchor design. I mean, I highly recommend, obviously, baseplate design because it gives you an additional check. But as Fetty is showing you now, that's where you get the software. Go start the free trial, play around with it. Reach out to us thereafter, give us feedback if you have questions, if you'd like training, and we'll come out and assist you. Another quick question, just to quickly cover a few here. Dane McGilway, apologies if I didn't pronounce your name correctly. Dane, this is a fantastic application. What I can say is this is another conversation, so please reach out to us directly or reach out to me. And we can help you with this this design, or we can look for a possible solution. Mohammed Alam asks whether it's possible to design stiffness as well. And
by the way, just to add to Dane's question, I mean, we have a lot of marine designing customers, etc. I'm from Turkey, by the way, originally. So, and I was also a specification engineer back in Turkey. So, the 3 biggest specifiers in Turkey who does marine structure were always doing this anchor designs or baseplate designs with us. So, as a reference, so I'm sure that we can find a solution to whatever the question that you have there.
Sure, thanks. Then feel free, please reach out to me on LinkedIn or just pop me a message and we can chat about this. Raymond had a question. With your design example, were the thickness of the base plate the same? Yes, Raymond, it was. And he comes to a conclusion, that he presumes the rigid method would lead to thicker base plate. And that's an important and great observation. yes, if you increase the thickness, you will approach rigidity. But then you don't, as Fethi mentioned, you don't want to have a 20 mil thick base plate when a 10 mil would work. And that's where the savings and optimization aspect comes in. So in the example that Fethi showed, he used an 8 mil base plate. It done the analysis on both the 8 mil in rigid assumptions and finite element assumptions. And obviously it gave you a clear idea of what the solution was. He's gone and increased it now, and you'll see that it gives you a very different solution.
Yeah, first I did 8, now second I did 15, now I'm trying 30 and then see what happens, basically. As you can see, so it was 49%. Now, because it's 30 mil, it's basically down on the anchor forces because of the prying forces being reduced. And the difference is about 16%. But again, is it optimal? Probably not. So yeah, it's just case by case study of these.
And the big thing, Fethi, I think that one of the conclusions that was drawn, it allows you as engineers to make an engineering judgment. I think that's the best thing and the most important aspect of this. You now have data based on sound engineering principles from which you can make an engineering judgment. Good. We've reached 5, Debbie. There's a few more questions. Sorry, guys, if I missed your questions. Please keep posting them, and Debbie, you can send them to me, and we'll try and answer them, and you can post them on your LinkedIn page, possibly. That'd be fine.
Thanks so much, Rashawn. That's perfect.
I saw one more question, which I will really quick. Yes, it is possible to design stiffeners. As you can see, I've designed one stiffener, and you can also have a custom stiffener of your preference. Anywhere you want, you can add stiffeners.
Good. On that note, thank you so much, Fethi, for taking the time all the way from Dubai. Go and enjoy a nice dinner. Drink lots of water, because you did take us through quite an experience. Thank you, Paiman and Debbie, again, and for all the delegates for joining. I hope this was insightful. This sort of brings an end, bittersweet, to our 3-part advanced connection design series. Obviously, the recordings will be available. I've been chatting to Debbie and Paiman in the background. There's other topics that we have at Hilti. We don't just have anchors. We're investing a lot in BIM technology. We're investing a lot in post-install rebar software and solutions. There's fire protection. There's modular supports like Fethi mentioned earlier. So maybe let SAICE know what you guys are really interested in hearing about, and I'll arrange with the team that we do a future lecture with you guys. Thanks again, and thanks Fethi, and thanks to the SAICE team. Have a good evening.
Thanks everyone for bearing with us. Yeah, I hope it was really beneficial to you. Hope to see you one day in South Africa face to face. But take care. Thank you very much.
Thank you. Thanks, Rishan, and thank you, Fethi. I'd like to thank participants for joining us. Please do write to us. We do have a lineup of interesting lectures coming up, and we have constraints in terms of the availability of presenters, but we're trying to make it regularly as much as possible to have at least one lecture every month. But I do love to hear from you. If any specific topic that you feel we neglecting to present it in our lectures, or you like us to present it, please do write to us, and we find somebody which is a master in that field, and we'll present a lecture to you. But thank you very much again to our presenters and participants for joining us. Debbie, last question. There is a number of questions here. You do have the details for all the participants, so do they need to maybe drop you an email with the question, or you okay in terms of getting the answer and then forwarding the answer to the person that has posed the question?
Okay, Paiman, I have made a copy of all of the questions, and I also have the delegates' details.
Okay.
So maybe what we can do is, once Rashawn and Fethi have answered them, then I can just make a document that I send to all the delegates so that you can receive that info. I think that's probably the best.
Okay. No, thank you. Thank you very much, Debbie. Thanks a million.
Okay. Thank you,
Really
Rashawn and
appreciate
Feti.
it. Okay.
Thanks, Payman. All the best, and thanks to the delegates.
Bye.
Thanks, everybody. Have a good evening.
Cheerio.
Cheers, everyone.
Cheers.